Yeah, good afternoon, sir.
Very good afternoon. Can you hear me?
Yes, yes.
Yes, sir. Yes.
Okay.
How are you doing, sir? How are you doing?
Fine, fine, fine. Actually, I was in the impression that it was on Saturday.
Yes, sir. Yes, sir. No, no, no. Saturday is Sunday, right?
No, today is Friday.
Yeah, yeah.
So please
And
start.
yesterday I got duck double also.
Okay, okay. So can we start, please?
Yeah, we will start.
Good afternoon, sir. I'm Good afternoon, sir. I'm Radhika. I'm doing PhD under the guidance of Professor Dr. Producer and the co-supervisor Professor Grandhe, sir. My thesis topic is the material science. Today I am presenting PhD Bio 2025. The PhD title is Phosphate Polymer Type Sodium Metal Ion Vanadium Phosphate Glass Ceramic Cathodes for Sodium Ion Batteries Structure, Electrochemical Performance and Applicability. Here the metal ion is replaced by the nickel, copper and nickel and copper. The total thesis outline is divided into the total 8 chapters. Chapter 1 is introduction. In introduction, I explain about what are the different types of the energy storage devices are there. What is the battery and what is the working of the battery? What is the difference between the lithium batteries and sodium-ion batteries? In literature survey, it used the relation from that one I collected what is the relation between the specific capacity and current. What are the different types of the cathode materials are there? From that one, which one is the better for the preparation of the cathode materials for the sodium-ion batteries? So chapter 3 is the material synthesis and characteristics. So here for the preparation of the materials for synthesis of the materials, I use the different types of the techniques. So after that one coming of the nano powder, the characteristics are the which type of the characteristics are doing in this one. The chapter 4 is here sodium, nickel, vanadium, phosphate, glass ceramic cathodes for the sodium-ion batteries. Here the vanadium is replaced by the nickel. In chapter 5, the vanadium is replaced by the copper. Here it gives the relationship between the structure and electrochemical performance. And the chapter 6 is the structure and improved electrochemical performance by combination of the nickel and copper for different mole percentage. In chapter 7, by taking of the 4, 5, 6 cathode materials, I prepared the sodium ion full cell coin cell and what is the glass ceramic base, the anode and cathode, and what is the electrochemical performance of the full coin cell. The chapter 8 is the summary and conclusion. Here, what we are looking for. Nowadays, we know about the different types of the energy storage devices are there. In that one, we want the renewable energy storage. That energy storage is compulsory having these parameters, the high energy density, and affordable cost, safe, and long life cycle with the need for that sodium ion batteries. So that batteries are the compulsory need, the lightweight, small and compact devices are also need for these sodium ion batteries. So that is my research to develop for the energy storage devices for further generations. Here the introduction is we want that is compulsory alternate to the fossil fuel cells. It controls the greenhouse effects. The main theme is here the lithium is also the triple day by day and it is also the high cost every year. So that's why but we can using the lithium ion batteries in different energy storage devices in different purposes. So we can think about any alternative batteries for the replacing of the sodium lithium ion battery. So that's why the sodium ion batteries is also nearly relatable to for the lithium ion batteries because it, demand is high but availability is very less. So that's why I think about for the sodium ion batteries for the preparation of the sodium ion batteries in that. The main is here cost wise is also sodium is very less value compared to the lithium because nearly 30 times of the cost is the less compared to lithium. So that's why sodium is better one. So why sodium ion batteries? There are the different types of the batteries are there, sodium ion batteries, lead acid batteries, lithium-ion batteries. These are the parameters in that one. These parameters are the energy efficiency is also sodium energy efficiency nearly 100, nearly 90 to 100% it reaches, and the cost wise is very less and compared to the lithium-ion batteries, and it is also abundant, and energy density, the moderate energy density is there. So that's why sodium-ion batteries are the compared to the lithium better compared to the lithium-ion batteries. The sodium-ion batteries having the redox potential is nearly 3.07 electron, 3.07 volts. But also coming to the disadvantage, it is not suitable for the safe devices. So that's why, and also less weight is okay, but it is not suitable for all conditions. So that's why sodium-ion batteries is better compared to the lithium-ion batteries. So working with the battery principle. So battery is also a combination of the three terminals: cathode, anode, and electrolyte. Here the cathode is also having the positive electrode is nothing but the cathode material. The negative electrode is also called anode. Electrolyte is the middle one between the cathode and anode. Here the electrons are transferred from the cathode to the anode, that is the charging process, and electrons are transferred from the anode to cathode, that is the discharging process. Here, so what is the cathode materials parameters? These cathode materials parameters compulsory having the stable structure and high specific capacity, high diffusion coefficients, and electronic conductivity is compulsory need for this sodium for the cathode materials. So in literature survey, the chapter 2. So in this literature survey, there are the different types of the cathode materials are there. Both three types of materials: P2 type, layer oxide materials, and polyanion materials. My work is related to the polyanion materials. Why the polyanion materials are related means there are the different types of examples are there for
Radhika, if all agree, can we directly skip to the result section where from the results start? If all agree, because I have very small time today. If all agree, because we have seen already or I expect that all the members have already seen this during synopsis and all, right? So
Okay.
if all agree, then we can skip directly to results.
Yes.
Okay. So in that one, polyanion is better, safe, and also the suitable for the operating voltages. So in this one, these polyanion components are suitable for sodium-ion batteries. So this is the
Yes, can go to. Yes.
So this is the results on discussion for the nickel cathode, the sodium nickel vanadium phosphate combination. The three samples are the mole percentages are X is equal to 0.1, 0.3, and 0.5 mole percent values. So it is the paper is published in the Journal of Material Science and Engineering in 2022. So there are the different types of the characteristics survey. One is the DTA, differential thermal analysis. Differential thermal analysis monitoring the TG, TC, and TM values, glass fashion temperatures, crystalline and melting temperature values. So here from these values, here in this graph, the dotted line indicates the glass ceramic glass value, and the thick line is indicates for the glass ceramic by increasing of the mole percentages from the 0.1 to 0.5. So by taking of measuring of all these values, first we can find out what is the glass stability parameter delta T value. So delta T value equal to TC minus TJ, and what is the KGL value? KGL is the average parameter value. So taking off all these values, you can observe in this table then which value having the ability parameter value. Delta T value is equal to high value 164 compared to the remaining two samples, and that KGL value equal to 0.53. So that's why 0.3 sample is the better one compared to the remaining two samples in case of the glass samples. And these glass samples are the heated at the crystalline temperature for 5 hours. In the glass ceramic materials are the coming there. In this one, the taking of the delta T value, ability parameter value, glass ability parameter value, that value is equal to 152. So this value is also high value compared to the remaining values. That KGL value equal to 0.35. So in glass ceramics value is 0.3 and glass value the KGL value equal to 0.5. So that is the best sample compared to the remaining samples in out of the three samples. This is related to the DTA analysis. By taking of these values, here the second graph is also related. What is the delta T KGL value by composition of the different mole percentages values. Here that one is the XRD analysis, the X-ray diffraction. So from this XRD analysis, you can find out the a crystallite, what is the size of the crystallite, and here the which type of the crystal structure is coming there from the taking of the lattice parameter values and angle values. A, B, C are the lattice parameter values along the X, Y, and Z axis values, and the inlet graph is also indicating the best sample of the XRD values. So from that XRD, you can find out the orthorhombic structure or which structure is the coming there in this one, and also calculated the interplanar distance value also there. So by taking of the WH plots values, then what is the stress and size of the sample value is also calculated here. You can calculate the average crystal size is calculated from the WH plots for the different samples. So entering all these values here in this table. So for the best sample having the three samples are having the crystal systems are the orthorhombic structures coming here. So in this orthorhombic structure, the A, B, C values are the different values, and alpha, beta, gamma values are the equal values. So that's why. So these orthorhombic structures are coming there in these samples out of the three samples in XRD analysis. The next one is the microstructure analysis, scanning electron microscope. So here some images for the three samples. The below three graphs are the indicated for the glass samples. The above three graphs are the indicated for the glass ceramic samples of the same image. So we can observe these samples. The X is equal to the first sample. X is equal to 0.1 mole%. Here the all the atoms are the located in different position, but compared to the X equal to 0.1, then X equal to 0.3. So before of the values in DT values, you can observe that sample having the glass stability parameter value. So in that one, the grains are interconnected in this one. So that's why the agglomeration is also very clear compared to the X is equal to 0.1 mole% and X equal to 0.5 mole%. Some of the variation is also coming there. So here, this is the cell image. From the cell image, you can identify what is the morphology of the atoms are the located in these samples, and what is the composition of which type of the composition is there inside of this sample. That is identified by using of the some images. Electron impedance spectroscopy EAS analysis. So here in this one, you can measure. I measured what is the bulk conductivity value, what is the charge transfer distance value is also calculated. So in figure A, here the impedance, real impedance values are imaginary values of the taking in at the X and Y Z values. So here inclined frequencies are the varying from the higher to mid frequencies nearly 0.1 Hz to 10.6 megahertz is frequencies coming there. In this one, you can calculate the bulk conductivity value is also calculated for the high frequencies. Charge transfer distance value is calculated from the middle frequencies, and inclined angle is also straight inclined angle is also given to the lower frequencies. So which is sample having the lowest charge transfer distance value, that sample having the high bulk conductivity value is also coming there. By taking of this formula, the conductivity sample formula is P by A into 1 by RCT. So here the X is equal to 0.3 is the best one. That sample having the lower distance value. So that's why automatically the bulk conductivity value is also high value for this best sample. So the figure B is also relation between the what is the bulk conductivity and charge transfer distance value by concentration of the different mole percentage values. The next one is the charging and discharging values. So here in this charging and discharging values for the first and 20th cycles of the three samples were at 0.10. So in figure 1, X equal to 0.1 mole%. The what is the discharge value and what is the charge value, that is also measured in this table. And then from this one, I measured what is the capacity losses coming there in the first cycle and what is the capacity losses coming there in 20 cycles. So by using of this capacity value, then what is the reversible efficiency coming there in first cycle and what is the reversible efficiency in 20 cycles. So out of these reversible efficiency, X is equal to 0.3 more% efficiency value is the high value. That value is nearly equal to the 92 efficiencies coming there in first cycle. And 95.13% is coming efficiencies coming there in 20 cycles. So compared to the remaining samples, this one is the best sample from this charge and discharging values. So the taking of the best sample, the X is equal to 0.3 is the best sample. The same sample is also the cycle levels is increases for every 5 cycles. For the first cycle, 5th cycle, 10th, 15th, and 20th cycles. By increasing of all these cycle values, then what is the charging value and what is the discharging value, and also cycle number is also increases. What is the discharge capacity value is also coming there. That is the measured in figure B. So the CV studies of the nickel cathode. So from figure A, it is related to the discharge capacity to the C rate. By increasing of the C rate, the discharge capacity value is also decreases. So C rate is increases automatically, discharge capacity value also increases. For the best sample value, the discharge capacity is also here. X equal to 0.3 is the best sample. In that one, what is the discharge capacity measured in that in figure A? In figure B, the C value is also increases from the 0.1C to the 10C. Then what is the capacity relation between the increasing of the cycle number from the 0 to 50 cycles? So cycle number is increases, then the C rate is increases, then the capacity is also decreases. Again, the C rate is regains from the 10C to the 0.1C rate. The battery, the capacity is also regained. So that's because the C rate is coming from the 10C to 0.1C rate. In figure C, by taking up the same best sample, the increasing of the cycle numbers from the first cycle to the 100 cycles. So at 100 cycles, the resistivity value is the low value. So that's why automatically the conductivity value is also increases at the best sample of the X is equal to 0.31%. So finally, CV studies, so cyclic voltamographs. So from that one, it is the gives the relation between the current and voltage. The graph is the potential window is maintained from the nearly 0 to 0.5 volts between come to the nearly 3.6 volt is also maintained. That type of the potential voltage maintained between the current CV graph. In this CV graph, identify what is the anodic and cathodic voltages values for three samples. Nothing but the oxidation and reduction values. By taking of the oxidation and reduction values, I entered all these charge transfer resistance values and conductivity values. So X is equal to 0.3 sample, the charge transfer resistance value is also high value. Then automatically the conductivity value is also increases. And the anodic and cathodic values also 2.18 and 1.82 volts for the best sample. The polarization value is equal to 0.3 volts. So the remaining values are the 0.42 and 0.47. For the best sample, polarization is compulsory less value. So which sample having the less polarization value, that sample is the best sample because the sample is also conductivity is also high value. So cathode compulsory high conductivity is also necessary. So that's why that is the best sample out of the three samples in the results of the nickel cathode. This is the first cathode. So this one is the results and discussion for the copper cathode. Here in this one, the combination is sodium, copper, vanadium phosphate. Here the vanadium is doped with the copper. These 5 types of the mole percentage. That's equal to 0.1, 0.3, 0.5, 0.7 and 0.9 mole percent. Here it is also just the revised version is submitted. Here, this one is the one of the capitation techniques, differential thermal analysis values. Here also the glass and glass ceramic values are also measured. In this one, the TG, TC and TM values also monitoring by using of the DT analysis. If the best sample is also having the, I entered all these values of the TG, TC and TM values. So delta T is the glass ability parameter value. Best sample having compulsory high values also there. So that's why 150, that is the high value compared to the remaining values in glass composition. So the KGL value equal to 0.3. So we can go to the glass to glass ceramic values. At the glass ceramic values also delta T value equal to 150. That value is also the high value compared to the remaining sample. So in glass ceramics, in glasses also, here also the X is equal to 0.3 the mole percent in the copper cathode. XRD, here the XRD identify different types of the phases is also coming there. Pure and impure phases are there. Here the some of the impure phases, the sodium NaV2, okay, the remaining are the pure phases. From these pure phases, and also here the peaks are also coming there. In that one, this one also can I identify which type of the structure is also coming there in copper cathode by taking of the different ABC and alpha, beta, gamma values. Here the orthorhombic and two types of the crystal structures is coming there in this one. One is the orthorhombic structure and second one is the monoclinic structures. So the orthorhombic structural values also and monoclinic values, that is parameter values are the different, and in orthorhombic structure alpha, beta, gamma values are also equal. So that is measured from this XRD. So microstructure analysis, SEM analysis. Here in SEM analysis, in this one in copper cathode, especially I calculated the particle size value is also calculated. Compared to the nickel cathode, in copper cathode, there are the mole percentages are also 5 types of the mole percentages are there. You can comparing the each one to one. the agglomeration is also increases and the particle size is also interconnected from 1 to 1. And taking of the x is equal to 0.3 sample, these grains are also interconnected from this one. By using of the image say software up to the 10 micrometers of the particle size is also calculated by using of these analysis. In this one, which type of the composition is there inside of the sample and what is the morphology of the particle size is also calculated by using of the microstructure analysis. So yes, and Nyquist plots is also calculated from this EIS analysis. The imaginary or impedance values are taken from in the x-axis and y-axis. Real and impedance values also there. Here in this one also, the bulk conductivity value or charge transfer distance values are also calculated from the high to lower frequency to the lower frequency is also calculated. At high frequency also calculated. Then we can find out the x equal to 0.3 sample having the lower resistance, higher resistance value, then automatically best sample having the lower resistance value, then automatically the conductivity is increases. So the relation between relation between the bulk conductivity and charge transfer distance values by changing of the different concentration of the composition of the mole percentage. What is the relation explained in the figure B? The same charging and the discharging profile. So here in this one, in nickel cathode, I observed the first cycle and 20th cycle, but some of the difference is coming here in the nickel and copper. So in the copper cathode, increasing of the cycles also, the first cycle to the 100 cycles. What is the charging and discharging values in the first cycle and 100 cycles? So the x equal to 0.1, 0.3, 0.5, 0.7 and 0.91 percentages. From this one, I calculate what is the efficiency value of the sample. So here, in this table, I calculated what is the capacity losses coming there in first cycle and what is the capacity loss coming there at 100 cycles. So finally, by using of the capacity loss value, what is the reversible efficiency coming there in first cycle and what is the reversible efficiency there in 100 cycles. So you can observe out of all these 5 samples, the x equal to 0.3 sample having the 99.3 efficiency is coming there at 100 cycle. In this figure, the taking of the best sample values also increases up to the 1000 cycles. First 100, 500 and 1000 cycles. Then what is the relation between the potential and capacity values and what is the charging and discharging value? The potential is also nearly greater than up to the 3.5 volts. Nearly it is reached to the 3.8 volts is also reached in the case of by increasing of the cycle numbers for the best sample. So CV studies of the copper cathode, and here the 4 graphs are related for the one is related for the discharge capacity for the C rate. By increasing of the C rate, discharge capacity is also decreases, and the increasing of the cycle number up to the 500 cycles are also increases. And compared to the cycle number, discharge capacity, and again the C rate is also interconnected. C rate is increases and the discharge capacity is also decreases. Again, the C rate is the regains from the 5 C rate to the 0.1 C rate. The capacity is also regains in the cathode. And the taking of the best sample, the cycle number is increases up to the 1000 cycles. At that cycles, then which sample, which side at the particular cycle, automatically the resistance value is also low value. So automatically that sample having the conductive value. So my motto is the best sample conductive value. So compulsory increases coming remaining out of the remaining low percentage values. So here x is equal to 0.3% sample conductivity is also increases compared to the remaining values. Then CV studies also. Here the anodic and cathodic values also calculated. Here the potential window is the starting from the nearly 0.3 volts to the 3.8 volts is also reaches. The potential window is maintained between these two values. The CV is a relation between the current and voltage values. So from these values, I calculated what is the polarization value from the anodic and cathodic values. So that is the polarization value is the low value for the x equal to 0.3 mole percent. That is the best sample out of the 5 samples in the copper cathode. The third cathode is the combination of the nickel and copper. The first one is only the nickel cathode and second one is only for the copper cathode. The third cathode is what is the efficiencies coming there by taking of the combination of the nickel and copper cathode. I observed some of the efficiency coming there in nickel, some of the efficiency coming there in copper. So what type of the efficiency is coming there by taking of the combination of the nickel and copper. So that's why I took the combination of the nickel and copper mole percentages for the different mole percentages, sodium, nickel, copper, phosphate. So the mole percentages of x equal to 0, 0.5, 0.711 more percent. So this paper is already, it is the published in Applied Physics in 2024. So from this here, I was taking of the glass ceramic samples, particularly DTA, what is the DTA analysis? So in this DTA analysis, what is the TZ, TC and TM values? Taking of all these TC, TM values, what is the glass ability parameter value? The glass here, X is equal to 0.7 more percent is the best sample, because the third sample is also having the glass ability parameter value, the high value, that is 46, compared to the remaining samples, that is the higher value. In the same sample having the KJ value equal to 0.51. So best sample compulsory stability parameter is also high. So that's why 0x equal to 0.7 is the best sample in the combination of the nickel and copper. So XRD analysis, here in the XRD diffraction, the three types of the phases are also identified, and what is the intensity value is also coming there by increasing of the more percentage. What is the relation between the intensity and peaks, and here the crystal size is also calculated. What is the average crystal size is coming there by using of the WH cuts. What is the stress and strain of the sample is also calculated by using of the XRD. So taking off all these values in the tabular form, same the two type of the structures are also coming there, orthorhombic structure and monoclinic structures are also coming there in the combination of the nickel and copper. So microstructure analysis, some scanning electron microscope. So we observed in previous, in nickel, some of the interconnected of the grains are coming there. Coming to the copper, so the grains interconnection is also increases. But here I took the combination, both combinations, the nickel and copper. Automatically, the grain boundaries are also, the inter of the grains are also increases. So you can observe the Ix equal to 0.c. In figure C, agglomeration is also increases. The particle size is also measured in this SEM analysis. So this is the difference between the nickel, copper and individually. But here this one, this is the good SEM image compared to the individual taking of the nickel and copper. This is the combination of the nickel and copper. So here in this one also, the what is the morphology is coming there by the combination of the nickel and copper. That morphology is also identified by using of the SEM, and what is the composition of the composition of the elements inside of this SEM image. So yes, analysis here in this one, taking of the real and imaginary impedance values on the X and Y axis. Here, due to the Nakish cuts of the semicircles from that one also. So X is equal to 0.7 more percent is also having the lower charge transfer distance value. So that's why that bulk conductivity is also calculated. That value is also high value. So measure all these values in this table. So X is equal to 0.7 more percent conductivity value is also the high value compared to the remaining value. That charge transfer distance value also the low value. So charge transfer distance and bulk conductivity, both the two are the inversely proportional to each other. So that's why which sample having the lower distance value, that conductivity is also the high value. At that time, the sodium and the intercalation and de-intercalation is also measured at the type of the glass ceramic anodes. That is possible at X equal to 0.7 more percent sample. Here the charging and discharging profile of the first cycle and 100 cycles for the X equal to 0.1, 0.5, 0.7 and 1 more percentages. By taking off all these values, then we can calculate. I calculated what is the reversible efficiency is coming there in the first cycle for 100 cycles. For the first cycle, the reversible efficiency is also 96.7% is coming there in first cycle. Reversible efficiency for 100 cycles is the 96% is coming there at 100 cycle. That is X is equal to 0.7%. So now this value is also high value compared to the remaining sample. So that's why this is the best sample in taking of the combination of the nickel and copper. So the taking of the same best sample, then what is the potential and specific capacity also for the up to the 1000 cycle, first cycle, 100 cycle, 500 cycle, and the 1000 cycles. By increasing of the cycles, nearly 3000 is also increases. The saturation of the efficiency is also reached in that one. Relation between the specific capacity and Coulombic efficiency by taking of the different cycles. That is also observed in all these samples, but the best sample in taking a combination of the nickel and copper cathode. So in CV studies of the nickel and copper cathode. So here by taking of the CV studies, from the fourth figure, the CV study, that is also the very important one. That one already like the previous, you can calculate. I calculated what is the polarization of the best sample of the nickel and copper. That is 0.45 oxidation and reduction values. So 3.28 volts and 2.83 volts are the coming there from the CV graph. Then the polarization value is equal to 0.45. So 0.45 value is the less value compared to the remaining polarization values. So this is the best sample. X equal to 0.7 is the best sample from the CV studies also measured. So finally, this is the result and discussion of the full cell. So I prepared the full cell by taking off the three cathode metals. First cathode is the sodium nickel, vanadium phosphate. That is the cathode material. Sodium perchloride, electrolyte, hard carbon is anode. That is the full cell one. That is I designated. I indicated that is the design one. Going to design two. In design two, the combination is the cathode is sodium copper vanadium phosphate. That is cathode. Sodium perchloride is electrolyte. Hard carbon is anode, that is design 2. Then going to the design 3, that is the combination of the nickel and copper. Sodium, nickel, copper, phosphate, that is cathode, sodium perchloride is electrolyte, and hard carbon is anode. So why hard carbon is selected for the anode? This hard carbon anode is also having some of the advantages. The low cost and the operating voltage is high, and the large capacity is also maintained. So that's why hard carbon can be treated as anode, and these are the three cathodes, and sodium perchloride is the electrolyte. So these are the parts are inside of this full cell. Negative case, spring, space, and a hard carbon, that is anode material. Separate. The next one is the NaCl4 electrolyte. The one is the combination of the nickel cathode, and the second cathode is copper. The third cathode is the combination of the nickel and copper. The last one is the negative case. So these are the labels indicating for the design 1, design 2, and design 3. My motto is next by taking of these full samples, these three full samples, what is the electrochemical performance is coming there by taking of the different types of these three cathodes. So these are the electrochemical analysis for the three full cells. First figure A and B are the related to the charging and discharging values are the at 0.10. So you can observe that design 1, design 2, and design 3. Design 3 is the combination of nickel and copper. So design 3 potential value is also the high value, and also the specific capacity is also nearly up to the 120, 180, greater than the 115. Nearly 118 is also coming there in case of the design 3 compared to the design 1 and design 2. Then the same sample is also increases up to the 1000 cycles. These three full cells are also increases up to the 1000 cycles. What is the relation between the specific capacity to the cycle number, and what is the relation between the Coulomb coefficients and cycle number? The design 3 is also increases in the specific capacity is also more, and efficiency is also more. So that's why we want that combination of the nickel and cathode efficiency is Coulomb efficiency also more in observed in these previous results also. That's why the same combination is also observed in the this full cell is also there. The same three designs is also Nyquist parts are also coming there. In that one also, in design 3, the lowest resistance value is also coming there. So that's why automatically the high conductivity is also there coming in design 3. So that value is also measured in this tablet form. And after the CV studies also observed for the by three design values. So design 3 is the combination of the nickel copper. Here also anodic and cathodic values also there. We're taking off the anodic and cathodic values. What is the potential value is also calculated, and the same samples are also by increasing of the time up to the 300 hours. The potential, there is no variation in the potential. Same potential constancy is maintained up to the increasing of the time. So that's why the design compared to the design 2, design 1 and 2 at room temperatures at the 0.10. So what is the conclusions for the half cell data? So these are the first half cell is the nickel vanadium, second half cell is the copper vanadium, third half cell is the nickel and copper. These are the parameter values, the voltage value, the combination voltage value also high value, nearly reaches from the 2 to the 3.8 volts. Coming to the specific capacity, that combination of the nickel and copper, that value also reaches to the 130 compared to the remaining ones, that is also high value. Specific discharge capacity value is also nearly 126.4, that is high value. Energy density is also 1.4, the high value, and life cycle is also can maintain up to the 1000 cycle also. So that's why this is the half cell conclusions of the half cells of the out of the three samples. The concluding remarks comparing the reported data. So it's the full cell data. What is the final reported data? full cell. First full cell design one is nickel vanadium phosphate. Charge capacity is 103, discharge capacity is 99. That efficiency is reaches up to the 95%. In the second sample full design is sodium copper vanadium phosphate. Here in this one, the charge capacity is 98, discharge capacity 92, efficiency reaches to the 93. The third design is combination of the nickel and copper. Charge capacity is 121, 117 in discharge capacity. Efficiency is also 96. So already in previous results, so the same combination of the nickel and copper high efficiency is coming there in the same also. In the full cell also, that type of the efficiency is also increased compared to the remaining full cells. So that's why this is the better one. The combination of the nickel and copper full cell is better compared to the remaining two full cells. Individual nickel and copper compared to the individual and nickel copper, combination of the nickel copper is better one. So that's why automatically that efficiency is also increases compared to the remaining samples. So this sample is comparing the recent reported data. So in that one, that efficiency is also reaches up to the 86.5% and charge capacity 96 and discharge capacity is 93. But in my work here, the charge capacity, discharge capacity and efficiency is also one. So compared to that one here, the nickel copper combination is the better compared to the reported data.
When was it published?
Published.
When?
Full set.
This recently.
2020. 3 years. So this is the comparison with existing literature here. From the literature survey, this graph is from the literature survey. What is the relation between the voltage and capacity? So there are the different types of the cathode metals and the combination of the sodium, cobalt, phosphate, pyrophosphate, different types of the metals are there. But here my sample is the place that one is, but it is nearly equal to the 120 capacity. Nearly 118 milliampere hour per the gram. That is the capacity, and the voltage is it is reaches to the 3.8 volts is there. So that is my position compared to the existing literature survey. Combination of the sodium, nickel, copper, phosphate. So what is the feature scope? This is the feature scope. The sodium batteries are also using the helicals, and the next work is it is not applicable for the room temperatures. At elevated temperatures, we are also using the sodium-ion batteries. So these are my publications. Chapter 1, 2, and third one is the revision must be submitted. The first one is published in the Journal of Materials and Engineering field. The second one is applied physics field. So these are the international conferences and seminars attended and recent also attended. These are the workshops and webinars. So heartily acknowledgement to the Professor D.S. Vice Chancellor Geetam Devu to University Hyderabad and Dr. Mohtar Reja, in-charge Principal School of Science, Geetam Devu University Hyderabad, Dr. T. Vishwam Sir, HOD of Science Hyderabad, Dr. Committee, Professor Subramanian Sir, XPS, IIT Hyderabad, Dr. Surendra Kumar Martha, IIT Hyderabad, Dr. Rajesh Kumar Sir, Scientist, CMET Hyderabad, Dr. Partha Voce, DMRL Hyderabad. Thank you.
Dr. Ayush?
Yes, sir. Radhika, have you included the questions from examiners in your presentation?
Yes.
I am asking, have you prepared the response to examiners?
Yes.
Yes, sir.
So please go through that.
So the first question is what is the typical information depth that can be obtained from XPS?
Yeah.
Sir, the questions were emailed to you, sir.
Yeah, I also have the questions, but I am just asking that whether she has prepared a response through slides or she will be responding them orally.
Orally she will.
Okay.
Yeah, she has prepared A4 sheet. And then if you ask any questions regarding, at least you can select among 4 or 5 questions from them, obviously she can answer for that.
Okay. So yes, sir, someone has started asking, no problem. Anybody can ask. Anybody from you. Because it will be clearer to listen her.
First you start, sir, any questions? After
Okay,
that,
okay, okay. Okay. So first question, as someone narrated, what is the typical information depth that can be obtained from XPS? Yes, Radhika.
From experience, to identify the elements and their oxidation states.
Okay. Second question is it possible to do the XPS measurements with variable energy incident photons? If so, what is the advantage of doing such measurements?
Yes, sir, it is possible by increasing of the varying of the photons also. It is also can identify what is the depth of the sample also. That is also the signal is also penetrating inside of that samples by increasing of the
So what-
photons.
Photons with what energy do you use in this experiment? Photons with what amount of energy?
Integral multiples of the energy, sir. HNU to HNU like that one.
Okay. Third question is what is the origin of satellite peak in XPS data?
In that one, what is the absorption? The losses is also interaction and losses is also identified from this photo emission of the absorption, sir. Interaction and losses process are coming there by photo emission process.
So these are electronic transitions or what?
Yes, sir.
Okay. What is the meaning of melt quenching monitored by ball milling?
The melt quenching followed by the ball milling, it can observe the stable class A phase is also identified by applying of the external mechanical stresses.
Okay. How the DOS and PDOS are calculated? The computational details seem to be missing. The reviewer says
sir.
that how the DOS and PDOS are calculated, and he says that computational details seem to be missing.
The DOS is nothing but the density of states, sir. PDOS means nothing but the projected density of states. These density of states are also related to the what is the electronic structures are there in energy levels and what is the orbitals in SBDM, SWR, different types of the orbitals also. What is the structure is also coming there from this configuration of these energy states, sir.
So these are calculated computationally through some software or what? Or some experimental.
Software, sir.
So he says that these computational like calculations are missing. Is it so?
Actually, I took help from other persons also, sir.
Okay. Right. So maybe you have served them directly without much detail or what.
From the Chennai, CLRI, from the Modi Dixit group, I took help from that person, sir. For the computational data.
Some corrections he has suggested, maybe you have made those corrections. Some okay. So my questions were different. Maybe like I have some different or small questions this time, which are not directly with some results, but comprehensive questions. For example, so what would you suggest the overall best composition for designing a cell or battery? What material, what composition would you suggest?
In this suggest the combination of the two elements is the better one, sir, compared to not the individual. I took individual nickel, individual copper, but finally from these coming these results, combination is better when taking of the
what is the
individual.
total composition? Tell me.
Sodium, nickel, copper, phosphate.
How much? How much?
Yeah.
Efficiency.
Composition, total composition of rest composition.
Sodium, nickel, 0.3, copper 0.7, PO4. X equal to 0.7 mole%, sir. That sample is the best one.
Okay. So what is the meaning of writing is 96% efficiency for a cell? Means this is what is comparison? Lighting 96% efficiency. For example, in a cell we say 10% efficiency means in comparison to received photons, and in a cell, what is the meaning of saying 96% efficiency?
Taking of the capacity and discharge capacity, sir, that one also I calculated, sir, not directly. So taking of these values, then I calculated efficiency, discharge capacity minus charging capacity, and by discharge capacity 100. That formula only I calculated the final 96% is coming there, not directly from the calculations only.
Okay. So as I could see that some XRD data are very means very clear without much noise, and some XRD data are full of noises. So what is the reason?
It is also combination of the crystalline and amorphous cell. And due to the some of the errors in peaks are also there, sir. Due to that, that type of the deviation is also coming there.
So what was the say average crystallite size?
Yeah.
Average size of the crystal in your samples estimated through XRD or same. What was that?
The average crystal size is calculated from the WH plots, sir, coming of the XRD by taking of the formula. D
How much?
How much?
Average.
58 nanometers.
So in this, I would like to make some comment that XRD and same are not very
Yes,
much
sir.
reliable for estimation of
Yes,
sizes.
sir.
Like
Yes, sir.
sizes calculated by these two are not comparable. They
Sir, I have a question.
differ a
here.
lot.
So actually, the XRD is kind of a mixed base as I can see. So you cannot translate.
No problem. No problem. In further studies, he can take care of that. No problem. Balaji sir. No problem.
Yeah.
In future,
Yes,
he
yes.
will take care of that.
Yeah.
XRD is also calculated for the single crystalline size. But taking of the sum, it is also possible for the particle size. So that's why only the single crystal only the values are the nearly equal. But here my work is related to the polycrystalline. So that's why some mismatching is coming there in XRD and sensor.
Okay. So Dr. Victor Levin from Spain, he has not asked any specific question, right? So last question from my side is that out of 3 designs of cells, right? 1, 2, 3 you have suggested. So
Yes,
what is
sir.
the difference between these 3? 1, 2, and 3 fuse cells?
First design is only sodium, nickel, vanadium phosphate cell. Second design is sodium, copper, vanadium phosphate. Design 3 is the combination of the sodium and nickel copper. Sodium, nickel, copper, phosphate.
Okay, so first and third seem to be almost same, except only the composition of this neodymium, I suppose, right?
The third one is the combination, sir. Combination of 1 and 2, then the 3 is coming there.
Right. So overall, the work has been done in a very, let's say, well way. But why you could not publish your papers in good number of journals or say good reputed journals? What was the reason? Only 2 you could publish, and the volume of work done is so high.
Yes. I increase it, sir. In further also, the paper is also the
Think
revision.
about
also.
that and like try to publish the work at the earliest, right?
Okay, sir. Thank you, sir.
This is all from my side. Thank you. Balaji sir.
Thank you. Thank you for constructive questions, Rajesh.
Yeah, anyone else? Yes. Fine.
Yeah, I am from a different field, so I don't know much about the batteries. And I had some questions regarding the XRD only. So I noticed you have the mixed phase in the XRD, right? There are several 2 or 3 phases in the XRD. So and when there is mixed phase, can you really apply Williamson Hall plot in a mixed phase? That's my question.
These are the William Hall.
I know, I mean, what you are measuring from Williamson Hall plot?
I measured the average crystal size is calculated.
Crystallite size, right?
Yes.
So.
Difference will come from the division.
No.
So Williamson Hall.
That's better.
It's a better way, but
Yes.
yeah, now thing is, since there are different crystals, like one is NaCuPO4 phase, another is the second one, third one,
Okay.
so if you take an average, can you really put Williamson Hall plot here? I don't think so, because different phase or different crystallite size, so. Really what you are trying to do is 3 equations are there and you are merge it up and try to.
Not
keep it in one.
separation.
If you go to your 14th page, your 14th slide. Yeah, see those electron side, your right hand side. See the points are all over the place on the graph.
In RRM one, some Ramesh sir asked, this type of Ramesh plots is not good, not correct. So that's why I revised that. It is published in RRM one already, the same graph is coming there. At that time, it is already published. In that, Ramesh sir, this is wrong. So you do not draw like this one. So that's why I changed that one. In RRM one also, you observe in the same graph is there. At that time, it is published in here. So revised version is submitted. Sir told it is wrong. Not wrong, it is not good. You followed another way. So that's why I changed that pattern. So that is the difference between these WH plots, this one and that one.
And the WH plots, we are taking only one phase of the compound, not for the mixture of the compounds. But in your Excel, it sees that the mixture of compounds, not
That
everything.
is exactly question is so.
But we can't plot that one. If you want to take any one phase, sodium, nickel, phosphate, and that one. So we need to take only that one phase and then we can draw the WH plot. But if you have the mixture of compound in the your sample, we can't draw for the WH plot.
These are field basically. That's why there are so many points distributed almost homogeneously over the graph.
Yes, sir. Different types of the points are distributed due to the errors. Different types of the points are there. But I measured the average crystal size only. So that's why
What kind of error? Error you said because of error in XRD or something, right? What is the error you are saying?
errors are not calculated due to some errors. The deviations are also
It cannot be any error. In intensity maybe something, but error means when you're talking about peaks.
like nothing but error means impurities. Impurity phases is also coming there. Purity and impurity phase also. Impurity is not here, and here V2O5 is also there. That is impure phase.
Which one is impure phase?
NaV2O5. If it is the combination of the nickel and phosphate. So that's why from that one the deviation is coming there due to the errors.
So if I am getting that sodium B2O5, that means you whatever you're expecting, the phase is not formed.
Nothing but until some of the impure phases are pure phases and impure phases are also there. So due to that when some of the error is coming there in that case.
There are two things. Either to enhance your application of properties of point of view, we disturb the perfection of the crystal or the compound. If you have some defects, then it exhibits some interesting properties. So are you doing intentionally doping impurities into the phase, or the compound formed itself is a mixture of it? That is a problem. Generally, when you go for any property measurement, the compound should be in the pure phase, single phase. The question is, that is what is question, whether it is a mixture of phase.
Why which type of error is coming there? So that's why.
That is okay, that's another question, but question is, it should be single phase, or intentionally you are disturbing the phase to make it impurity so that we can create. So what is your interest?
Taking of the impurity, but some of the impurities or some of the that type of the phase is also there. So like that one, I indicate that one also in
Normally, she want to try to make a single phase. But along with that,
Nothing but you have to go for the temp, and after them HKL values has to coincide, and which one is more coinciding, we have to check. That cannot be done by external. So what they are saying is, we have to go for temp. Then data, if you are having those, then we can coincide more effectively for the particular field.
Yeah, so it's not. You're on effort error, right? I mean, the saying error, but some unwanted phases are also be observed. Why supposed when there are 3 or 4 phases like this, you cannot. Yes, yeah, Williamson for because the strain will be different. So Williamson on the FWH will be different for different crystallization. The second one, I just have another thing. Just from the ACM, what you are measuring, you said some crystallite size or something.
particles.
Both are not comparable, right?
Yeah.
Crystallite size and particle.
That is different distance.
Based on it. How they are different?
Combination of the crystals then the particle is coming there. Sir.
No, what is the difference between crystallite size and particle?
Particle is some of the low value compared to the crystallite value. So that's why I took the microstructure value for the calculation of the particle size.
No. Crystal means group of atoms.
Oh,
Particles means group of crystals. So definitely there is a change.
Yeah, this.
If your particle size is exactly as the crystal, then we can call both are same. But the group of crystal, we can get the particle size means always the polycrystalline of the material. So that is the particle. Obviously it is higher than crystal size calculated from the Excel.
yes, sir, I told that one only. These two are not equal, different.
Yeah, why it is the difference? Are asking why it is the difference. So that's why this is the group of atoms in the crystal. Is it right?
Yes,
Yeah, particles means group of crystals.
yes, sir.
So that is the main difference.
So group of the crystals automatically the orientation is different. Different types of the orientation is there automatically. The value is also different.
Yeah, particles will be larger than
Yeah, many done.
My one question. So you are making the three different systems. One is the nickel, other one is copper, and the next one is nickel and copper. But there is a missing in the vanadium.
Yes, sir.
Why you are missing that?
I observed this type of the sample. I calculated from that one also. The results are not good like that one again by taking of these two samples. In the place
When you are taking the individual nickel, vanadium, sodium, nickel, vanadium, and phosphate.
Yes.
Second one is the nickel, sodium, copper, and lead. So when you are taking those things, it shows the some activity. And when you are taking the bimetallics, you are missing the vanadium. What is the role of vanadium in the after two samples?
In that one, the oxide, the nickel ions are the replaced by the vanadium, tetrahedral vanadium. In this one, the nickel, the copper ions are the replaced by this vanadium. But here the vanadium is not mixed. Here they are the intermediate phosphate. The role is taken by the phosphate in this combination.
In the previous also phosphate is there. Vanadium phosphate is there.
Yes, phosphate is there, but here extra vanadium is there, replacing of the copper. I took like that when I selected like that samples compared to the literature survey.
Okay, vanadium is replaced with the copper or nickel, whatever.
First two samples like that ones. I told like that same one.
If you have the vanadium, there is charging band in this. Vanadium also, there is charging band.
Okay. Any more questions? The answer, the questions are over here. Now, if you can just recommend the candidate for the PhD.
Hello. Yes, sir.
Hello, sir.
Okay, it was nice to see the work, and also I'm excited to see practically how the cell is formed or how this whole activity goes on. Nice work. Radhika, congratulations for getting PhD.
Thank you.
Everyone who was related with Radhika, congrats to them also.
Yes, thanks.
Thank you, Dr. Ayush. And
Okay, sir. Hello.
related formalities from Gitan's side regarding the
Hello.
signatures and.
You can send me, no problem.
Yes, sir. Regarding the, yeah, sir, please declare PhD degree and you should call.
Yeah. Based
Radhika
upon
as
the okay. So based upon the presentations made by Radhika before the committee and her response to the queries, I recommend Radhika to be awarded with a PhD degree from Gita University. All the very best, Radhika, for your future work.
Thank you, sir.
Thank you.
Okay.
Dr. Ayush.
Yes.
Yeah, the formalities from the Gitam side will reach
Okay.
you by tomorrow, day after tomorrow. And
Right.
where signatures, right? Not only the report side, but also towards the handling side.
Okay.
Please, as soon as possible, and then we'll get back to you.
Right.
Thank you very much, sir. Thank you very much.
Thank you, everyone.
Thank you for your valuable
Thank you so much.
time that you have spent and give good advice to the student, right?
Thank you. Can I leave now?
Yeah. You can.
Yes.
Right.
Okay, thank you so much. Thank you.
Now Thank you, sir.
తీసుకొచ్చి కానీ ఎక్కువ
And then
Not there.
I remember 20 years.
The same college, 18 years.
We are in charge.
Yeah, so when copper is there, because you are reading copper solution, China, so there will be one, that is to be. Not for all like this. So that period is adjacent to another thing.
If I don't.
If the linear having new solutions, you are trying to find
Partnership. Obviously, it is giving instructions. There is no point of single phase. That's why I got my answer.
Press note like that. India trial abstract. Press note trial. Press note and trial. Abstract thesis. Press note and ఇది తీసేసి పైన ప్రెస్ నోట్ అని పెట్టి సేమ్ ఇదే పెట్టేసి ఒకసారి ఇంకో ప్రింట్ తీసి అబ్స్ట్రాక్ట్ తీసేసి ఇక్కడ పైన ప్రెస్ నోట్ పెట్టి ఇదే పెట్టండి ఇక్కడ కొంచెం గ్యాప్ ఇవ్వండి పైన మీరు ఢిల్లీ రండి ఈ మంత్ 20 తర్వాత ఫస్ట్ వరకు అప్పుడు 2 రోజులు ఇచ్చినా పర్లేదు. నో ప్రాబ్లం. అప్పుడు చేస్తాను వెకేషన్. సరే.